This presentation is on the sum to infinity for geometric series. Lesson objectives. To understand the concept of sum to infinity. To be able to use the sum to infinity formula for geometric series to solve problems. So, to derive the sum to infinity formula, we start with the formula for the sum of a geometric series. So Sn is equal to a times 1 minus r to the n all over 1 minus r. Then we multiply out the bracket, so we get a minus a times r to the n all over 1 minus r. Then we break it down into two different fractions, so we get a over 1 minus r minus ar to the n all over 1 minus r. Now at this point we've rearranged it so that one function has no n in it and one function does. So now to do the sum to infinity we let n tend towards infinity. Then if r is between minus 1 and 1, r to the power of n would tend towards 0. For example, if r was a half, then r squared would be a quarter, r cubed an eighth. So we'll get closer and closer and closer to 0 as n increased. And therefore, the second expression will also tend towards 0, as ar to the n over 1 minus r would be basically 0 times a over 1 minus r. So we'd be left with just the first fraction as n tends towards infinity. So s infinity equals a over 1 minus r, and this is the sum to infinity for a geometric series. And this formula is in the formula booklet, so you don't need to be able to remember it. Example 1. For a geometric series with first term 12 and common ratio 2/3, find the fifth term, the sum of the first 8 terms, and the sum to infinity. So starting with the fifth term, we identify as a is equaling 12 because that's the first term, r the common ratio is equal to 2/3, and n for the fifth term is 5. Now we need to make sure we're using the correct formula. We want a term, so we want the un formula. So un is equal to ar to the n minus 1. Sticking in our values, u5 is equal to 12 times 2/3 all to the power of 5 minus 1. Sticking all that into calculator, we get that the fifth term is 64 over 27. And in pure maths, it's perfectly acceptable to leave that as a precise, exact answer. But if you were asked around it, it is equal to 2.37 to 3 significant figures. Now, the next part, we want the sum of the first 8 terms. So a is still 12, first term is unchanged. r is 2/3, the common ratio remains unchanged. But now n is 8 because we want the sum of the first 8 terms, and we're looking for a sum, so we've got a keyword sum, so it's the Sn formula that we need. So Sn equals a times 1 minus r to the n all over 1 minus r. Sticking in the values, S8 equals 12 times 1 minus 2/3 all to the power of 8 all over 1 minus 2/3. The exact answer we get for that is 25,220 all over 729, rounded to 3 significant figures, 34.6. Then the next stage is to find a sum to infinity. So sum to infinity, the a is equal to 12 still, the r is equal to 2/3. The sum to infinity we don't need an n. So we go straight to the formula. Sum to infinity equals a over 1 minus r, which is 12 over 1 minus 2/3. Calculating, we get 36 exactly. Second example. The sum to 4 terms over a geometric series is 15. And the sum to infinity is 16, and we're to find the possible values of r. for part A. So in part A, RA we don't know, R we don't know, N is 4 for sum to 4 terms, and our sum to those 4 terms is equal to 15, and the sum to infinity is equal to 16. So starting with the Sn equals 15, if Sn is equal to 15, then that means that we can place Sn with the sum to n terms formula, so A times 1 minus r to the n all over 1 minus r is equal to 15. Sticking in n equals 4, A times 1 minus r to the 4 over 1 minus r is equal to 15. And then we do the same thing with the sum to infinity. So the sum to infinity is 16. Replace the sum to infinity with its formula. So A over 1 minus r is equal to 16. Now we're then able to substitute the A over 1 minus r equals 16 into that left-hand side equation. As we could rearrange the left-hand side of the equation into A over 1 minus r times 1 minus r to the 4 is equal to 15. So we can replace the A over 1 minus r at the front with 16. So you get 16 times 1 minus r to the 4 is equal to 15. Rearranging, divide both sides by 16, we get 1 minus r to the 4 equals 15 over 16. Therefore, r to the 4 equals 1 over 16, because 1 minus 1 over 16 equals 15 over 16. So r equals the fourth root of 1 over 16, which is equal to a half or minus a half. So that's the two possible solutions. Just like a square root gives two possible answers, so does a fourth root. And then looking at B, we're told that the sequence is positive for B. So r equals a half. As r equals minus a half would have given us some negative terms, so it would alternate. Because of the minus and the timesing each time, the sequence would alternate between positive and negative values. Now we can stick our r equals a half into either the two expressions we started with, but the easiest one by far to solve would be a over 1 minus r equals 16. So we substitute our half in, a over 1 minus a half equals 16. 1 minus a half is a half, so we end up with a divided by a half equals 16. Multiply both sides by a half, we get that a is equal to 8. This concludes this presentation.